Dear students, this is regarding the topic what is known as equal area criterion, which is basically required to understand the stability of the system. Okay. So to understand the stability, generally we have to draw the swing curve, and from the swing curve we could analyze what is the condition of circuit. Okay. So this is what the first point to determine the stability, whether the system is stable or not. After a disturbance, it is necessary to plot the swing curve. So if these curves shows that the angle between the two machines, any two machine, tends to increase without the limit, then the system is stable. So like if we say that this is going to be the plot, this is going to be the plot of delta with respect to time. If there is going to be the continuous increase in the swing angle or the swing load angle, then we could say that the system is unstable. The system is unstable. Okay. So after the disturbance, if the angle between the two machines reaches a maximum and then decreases to a finite value, then we could say that the system is stable. So there must be a tendency to be observed in the system after a disturbance that there is going to be a larger vibration, and the vibration vanishes out and the system reaches the equilibrium condition again. Then I could say that the system is stable. Okay. So if I consider two machines are connected in parallel with a constant input power, no damping voltage Vg, the angle between the two machines either increases indefinitely without any control or oscillate about a constant amplitude. So these are the two conditions what would generally be observed when we connect the two machines in parallel, and there is going to be a fault in the machines. Okay. So there is a possibility of increasing the swinging angle continuously, or after a disturbance, there is some vibration and the machine returns to equilibrium conditions. Okay. So in either case, either the machine fall out of synchronism in the first swing or never. I can explain and I can throw some more lights on that. So let me say that there is going to be a disturbance applied on the system, and there is going to be oscillations like this. If my machine is capable of restoring its stability at the maximum peak overshoot, what you have discussed in the control system, if my system is capable of regaining its stability in the first maximum peak overshoot, I can say that the machine would never lose its stability after that. And this is called as a first swing. Okay. And you analyze the stability, and if the machine is stable in the first swing itself, then I could say that it will never lose out of synchronism. So this is what I have mentioned in this particular line. Either the machine will fall out of a step, in the first swing, or never it will lose its synchronism. Okay. Now, what is this equal area criterion? So instead of plotting the swing curve for a single machine connected to infinite bus or two machine system, the equal area criterion is a graphical method of determining whether the machine comes to rest with respect to each other, whether there is a possibility of having or regaining its stability or not will be identified by this graphical method. So this is applicable to all two machine system, whether there is actually a two machine or one machine connected to an infinite bus. So that infinite bus can be considered as an another machine to which I'm going to connect my machine. Okay. So this is applicable for any sort of a system, and this is a graphical method from which I could understand whether my system is stable or not. Okay. Now I'll start from this equation. So single machine connected to infinite bus. So there is going to be a two machine system. So I have a machine generator. I have a generator. This is my generator bus. Via a transmission line, this is connected to an infinite bus. So this is my infinite bus. Okay. So this is my SMIB, single machine connected to infinite bus. So what is my swing equation? H by pi f d square delta by dt square is equal to PA, which is equal to PM minus PE, where PM is the mechanical input and P is the electrical input. Okay. Now this H by pi f, I can write it as M. So my equation is modified as M into d square delta by dt square is equal to PA, which is equal to PM minus PE. And divide this equation by M. So I'll get d square delta by dt squared equal to PA by M. Let me call this is equation number 1. Okay. Now on either side of this equation, 1 multiplied by 2 into d delta by dt. So I want to simplify mathematical representation. So for that convenient, I am multiplying either side by 2 into d delta by dt. So 2 into d delta by dt, d square delta by dt square, this is equal to 2 into PA by M multiplied by d delta by dt. Okay. And this 2 d delta by dt into d square delta by dt squared, I can write it as d by dt of d delta by dt the whole square. Actually, when I differentiate d delta by dt the whole square with respect to t, I'll get 2 into d delta by dt and then function of a function, so d squared by delta by dt squared. Okay. So I end up with the equation d by dt of d delta by dt squared is equal to 2 PA by M multiplied by d delta by dt. Let me call this is equation number 2. So in the next step, if I multiply equation 3 by dt, so I'll end up on the left hand side d by d of d delta by dt the whole square is equal to 2 PA by M multiplied by d delta. So let me call this equation number 4. And if I'm integrating equation number 4, d delta by dt square is equal to 2 by M, and this d delta, I have to take the limit as delta naught to delta, where delta naught is the initial load angle, is the angle between the two voltages. If I say that electrical voltage between the infinite bus voltage and the incoming bus voltage. Okay. So delta naught by delta, this PA multiplied by d delta, and the integration limit is delta naught. And if I take, if you remove the square on the left hand side, the right hand side is square root of 2 by M delta naught to delta PA. Okay. Now, what is the condition for stability? There should not be any deviation in angle with respect to time. Okay. And if my load angle remains constant, and I can say that my machine or my system, my power system is under the steady state operating condition. is a steady state operating condition. So condition for stability is d delta by dt equal to 0. Okay. So this will be equal to 0. So this will be equal to 0. So inside the square root, if you want to make that d delta by dt equal to 0, integration delta naught to delta PA d delta equal to 0. This is what a condition. So now this PA I can substitute as PM minus PE. PM minus PE. Okay. So what is this integration actually means? The integration actually means the area under the curve. So what is my curve? PA into d delta is the curve. And what is my boundary? Delta naught to delta. So therefore, PA versus delta between the limits delta naught and delta M. I can say that the maximum delta is the area under the curve PA versus delta. So now you substitute PA is equal to PM minus PE. So PA into DL delta equal to PM d delta minus PE d delta. Okay. Now, if I take this graph, the electrical power with respect to delta, the PM is the mechanical input, which is the horizontal line like this. Okay. And this PE versus d delta is going to be my angle, this power angle curve. So this is equal to PM sin delta or P max sin delta. Okay. Now, this PM into d delta is the area under the curve between the lines PM and this delta naught to delta M. So this is what the area under the curve representing my PM to d delta. Okay. And what is my PE d delta? If I take another color, this PE versus delta or PE versus PE to d delta represents the area under this point, delta naught to this point and this point and this point. So this will be the area under PE versus delta, PE d delta. Okay. So what is this equation? PM d delta minus PE d delta. And if I do the operation, this is my PM d delta from this point to this point. This point to this point is PM d delta. And this is the PE d delta. If I subtract, this is the common area, and therefore my curve will end up with the area like this. So if I do that, the subtraction between PM d delta and PE d delta, I will end up with the area mentioned by this. I just show what is this area. Okay, so this is the area hatched one, and this is the area. If I do the operation, PM d delta minus PE d delta. Okay. So if I do another simplification, PM d delta, PE d delta, if we take it to the outside, this PM d delta equal to PM. Okay. So this area A1 should be equal to area A2. When I look into this power, the mechanical power and the electrical power for this particular one. Okay. So for this area A1, for this area A1, this is my starting point. This is my starting point, and this is the area. Okay, this is the area. So at this point, this is the electrical power and this is the mechanical input. So the mechanical input is greater than the electrical output. So what will happen? My power is going to be an accelerating power because PM minus PE is positive. So therefore, it is going to be an accelerating power. And at this point, my electrical power is greater than the mechanical power. Electrical power is greater than the mechanical power. So what is my PA? My PA is equal to PM minus PE. P is higher. Therefore, PA is negative, which represent that is the deaccelerating power. Therefore, I can conclude this. If the accelerating area equal to the decelerating area, then I'm able to get my system under steady state operating condition even after a disturbance. Even after a disturbance. Okay. So this is what we actually seen here. So when if it just it's this. So let me take a string like this. I'm going to drop a pendulum, and this pendulum is about to move about the equilibrium point. Let me say that this is the extreme point A, and this is the extreme point C, and this is my equilibrium. Okay, and because of the initial force, the pendulum starts swinging. So that is going to be a forward and reverse movement like this, and because of the air friction, this movement vanishes and the oscillation slows down. And when the forward movement and the backward movement is equal, it is about to oscillate at a constant amplitude, or I can say that the pendulum regains its stability. So this is what actually happens in my machine also. So because of a fault, there is going to be an acceleration, and because of the acceleration, the load, because of the acceleration, if the rotor forwards more and backwards again, so there is going to be an oscillation about this equilibrium. There is an oscillation about this equilibrium point. It goes like this, coming back, goes like this, coming back. Okay, and if this accelerating area and the decelerating area is equal, after some time it will regain its stability and it operate at some point, maybe some other point. Let me say that this delta or delta. So since we are concentrating or focusing on these two areas, accelerating area equal to the deaccelerating area, this is called as equal area criterion. This is called as equal. So this is what I want to share. This equal area criterion is very important from the examination point of view also. So I'll share this particular recording and the handouts also. Prepare for this particular question. Okay. So in the next recording, in the video recording, I'll share another two important points, the derivation regarding the critical clearing angle and the critical clearing time. Okay. So what is this actually? So there is going to be a disturbance in the system. So in the previous problem we have discussed about there is a generator, transformer, there is a double line. Okay, and there is going to be a fault in the mid of the line, and the fault is cleared by simultaneous opening of the circuit breaker. Okay, now at which point I have to open the circuit breaker will be determined by this equal area criterion. Okay, so what is the condition for regaining the stability? Accelerating area equal to the decelerating area. Okay. So at which point if I open the circuit breaker, the accelerating area will be equal to the decelerating area. That is called as critical clearing angle. And the time corresponding to the critical clearing angle is known as the critical clearing time. We will do the derivation in the, and I'll do the recording and share that recording for the critical clearing angle and the critical clearing time.